requires TensorFlow and Keras. So just to show you how to install it, you just have to activate your environment, your MIE44 environment, and then just right-click install TensorFlow and Keras, and then run that. So that should run, and I'll start explaining image classification, and then we'll see where we go from there. Great. So everyone can see my screen now? Okay. So today we're going to introduce the image classification problem. So this is the task of assigning an input image, one label from a fixed set of categories. So for example, in the image here, we could all see that it's a cat, but however we want, yeah, thanks Yvonne for the instructions. We want a computer to be able to tell that this is a cat. So this is one of the computer vision tasks. I don't know if we're actually going to be doing object detection and segmentation in this course. However, this is just other tasks that we could do that are image classification. So in a computer's mind, each image is represented as an array of pixels, and each pixel has 3 values representing the RGB values of that color. So this is kind of a gray color. So that would have a certain RGB, red, green, and blue color. If it's black and white, then we could just reduce that to only one number, ranging from 0 to 255, which would be the grayscale, or just 0 and 1 if it's black and white, and those are the only 2 colors. So we can see that this ends up being a lot of numbers. So for an image of 248 by 400 pixels, and then 3 numbers for each red, green, and blue, we end up with like almost over 250,000 numbers. So the computer would have to read this and then determine whether it's a cat, a dog, a hat, a mouse. And typically we give them the labels before that it could be, like potential labels. However, yeah, exactly. Yes. Yeah, so some of these challenges involve, obviously not every cat looks the same. You're not going to have the same cat over and over again in a bunch of different photos. And also you might see the front of a cat on one side and then the back of a cat on the other. And how are you able to tell that's still a cat? So these are some of the common problems in image classification. Other problems is it might not be, in this photo, the cat is in the entirety of the photo. However, it could also be that there's just a cat in the bottom left corner and then the rest of it is something else. And would our algorithm still be able to tell this is a cat? Another thing we can see is deformation. So another data set we'll have is just handwritten digits. So someone wrote numbers 0 through 9. And obviously everyone's handwriting is different. So just because one looks like the one to the human eye doesn't mean it's going to look like other people's ones. And then there are other challenges here. I'm not going to go through all of them, but here are a bit of examples of the challenges. So viewpoint variation, this is all the same thing. However, it's from different viewpoints. Illumination constraints, darker versus lighter, but they're all penguins. Deformation, this cat is just funny. And background clutter, the cat is on a rug that has very similar pattern to it. So how we would go about writing an algorithm that classifies images. So we can't just like sort numbers, not that obvious. So instead we're going to go with a supervised approach. So we're going to have pre-labeled data. So these images are cats, these are dogs, these are mugs, these are hats. And then we're going to try to train an algorithm that could detect whether a new image that wasn't in this data set is one of these images, or one of these labels, sorry. So our input will consist of n images, each labeled with one of different k classes. So in this case, k would be 4, and n would be however many this is. And we're going to try to run the training set to learn what each class is and then test it on new data. So one of the common classification test data sets is the CFAR10 data set. So this is 60,000 images. They're only 32 by 32 pixels, and it's one of 10 classes. So here are the classes. Well, I'm not going to list them out. And so this is one we're going to start with. So firstly, we're just going to plot the images to show you what it looks like and how. So this is just an airplane. You can see that it's very, very pixelated because this is just 32 by 32 pixels. And yeah, so this is an airplane, I'm pretty sure. Yeah, label 2 airplane. Exactly. So this would be the body. So it is still tough for humans to be able to classify this, especially with very low resolution. But we could create algorithms that could have up to 90, I think 99.7 was the highest in CFAR10. We're not going to get that in this course, but that's possible in computer vision. And then another data set that we have is called the MNIST data set, which is I talked about it a bit before. Also 60,000 examples. And each of these are just handwritten digits. So I'll run this also just to show you. So this is just a random example, and this is the number 9. So we can tell it's a number 9. However, it's not. This is a white on a black background, and it could differ between images. So you can just look at another image if you want, just to see what it's going to look like. That's a 3 fuzz. It might all be white on black background actually for this MNIST one. But these are just people just literally wrote the numbers and then scanned them and sent them to MNIST. So the first algorithm we're going to talk about that is used for image classification is called the k-nearest neighbor classifier. So we spoke a bit about k-nearest neighbors in the last tutorial when we were talking about spectral clustering. And basically in spectral clustering, each data point would be assigned an edge to its k-nearest neighbors. So that's very similar to what we'll be doing in this, where each new image is going to be assigned just basically you're going to find its k nearest neighbors. So let's say we had k equals 1 and we have a new image. We're just going to find which of the images in the training set is the closest to our image in terms of a data distance metric that we're going to define later. And if we have k that is high, let's say we have 5 as our k, we're going to find the 5 closest images to our new image. And then they're just going to basically vote on which class it should be. So let's say 4 of them are dogs and 1 of them is cats. It's going to say, oh, it's going to be a dog, this new image. So for k equals 1, just the nearest neighbor classifier, and we're going to code that later on. And then so the distances that we're going to use, this is just the L1 distance. So basically take each pixel, or in this case, because it's black and white, I think there's only going to be one number per pixel. So basically you just take the difference and then you take the absolute value, which is just the L1 norm of the difference, which is the L1 distance. And basically you just sum them up and you find the pixel-wise absolute value differences. And then the closer this is to 0, the closer the images are together. So if it's exactly 0, it means you have the same image. And basically we're going to find the k closest images, which means the k images from our training set that are the closest to this new image. And then they're going to vote on it. Does that make sense to everyone? How does it work? Yeah, okay, perfect. And other distance metrics could also be used. We're going to go over using the L2 norm instead of the L1 norm just after this. However, we're going to start after training this. So basically, we're just going to set the x values to be the x from our training data and the y. And then for each value in our test data set, we're going to have to compute the distances, which is going to be done as an exercise. It's not actually 0. And then assign the predictors class. So this is going to be an exercise for you guys for the L1 norm, np.sum and np.absolute value useful. And then also for the prediction to just find the predicted class, just use a self to refer to attributes in the class. And I'll give you guys about 5 minutes. And if you need more time, let me know. Yeah, so as a you want to say x in this case is going to be number of samples is the first dimension, and then 372, which is basically just a flattened version. And I'll talk about why we flatten it later. But those are just the dimensions. Yeah, probably important to note. Here's the shape. Yeah, self.xdr will access the training samples, and then self.ytr will access the labels of those training samples. So it's been about 5 minutes. If you guys are finished, just write in the chat that you're done, and then if not, I'll give you guys a couple minutes. Done. Okay, perfect. So I'm just gonna copy paste the answers from the solution one. Okay, so essentially, the distances are just the L1 norm. So basically, we take the absolute value of the training set minus the x, which is our test prediction. So for each I is each range in each test. So basically, this will just be one of our test set data sets, and then this will be all its attributes. And basically, we take the absolute value of that, and then we sum along axis equals 1. So that means we don't want to sum along axis equals 0 because that is summing across each of the test sets. We want to sum across axis equals 1 because we want to sum across each of the pixels, so each of the 32 by 32 by 3. And then basically, we'll be able to find just one number that computes. So in the axis equals 0 in the first dimension, it'll be just each of the test sets, and then in the second dimension, axis equals 1 will be each of the distances. And then we basically want to take the, because this is just nearest neighbors of k equals 1, we just want to find the closest image. So find the index of the smallest distance as was given. And then basically we can just access from self.xtr is the training data set. So in the nearest neighbor class, when we define it here, I'll go through this part. So basically we have our training set and our test set. We instantiate the class, and then we essentially train the data set by just inputting x train, y train. So then we go to this function, and then self.xtr is just all of our training x values. So it is shape of number of our training values in this dimension. So, and then I could draw it. Let's see if I can annotate on the screen. So let's say this is just our thing. This would be training set. Oh, each row would be training set, and then in each row would be basically each pixel number. So this would be like 250. Sorry, my handwriting is not great on trackpad. And then this would just go on for 32 times 32 times 3, and that would just be an array. And this would be just the training data set. Does that make sense as to what this would look like? And then you have each different training example. So this is just each of these things. Change my color. Each of these things represents an image, one training image. So we'll have an n amount of these. Okay, great. So basically, we take the training data, we subtract our single image, and then this will give us, for each image, it will give us the absolute value of each pixel, and then we sum that along axis equals 1. So then we'll have basically for each, the distances will just be the distance from our current image to all the rest of the images, and then we basically take the index of that and then sub it into our y training data set because these indices would match. Obviously, this one finds the closest indice of our x's, so the closest image, and then this will basically find the corresponding label to that image. And we set that to y equals 1, and then we do that for each of our tests. So one important thing to note is that we flatten these images. So essentially, instead of being actually, in this case, there is the ×3, which means that the images are colored and not grayscale, so they have RGB coordinates. So this example is not necessarily correct because it would be 3-dimensional. Like this is just for grayscale. But an important thing to note is when we're doing this, we're flattening it, which means it doesn't really matter where the pixels are. There's no difference between a 32 by 32 image and a 16 by 64 image. Yeah, like it doesn't. What the image looks like doesn't really matter to this. It doesn't matter that there's a pixel underneath. Like if we go back up to the image of the cat, this part of the eye won't actually be right underneath it in our algorithm. It'll be somewhere along here. So we're just really looking at a pixel by pixel composition of the image, and we're not really looking at where the pixels are relative to one another. So that is this is a reason why, like in neural nets, you can see like convolutional neural nets, which do take into account the locality of each data point for each pixel. However, we're not going to cover that here. So just that's an important thing to note that there are some limitations when you flatten data and when you're using just algorithms like k-nearest neighbors or MLPs, which we'll do later, and logistic regression. So essentially, I'll run this. This might take. Oh, I didn't run this part yet. It might take a little bit of time to run if you're following along at home because this is pretty like intensive I think it might be like a minute to run for some of them, especially when you're doing the prediction. The training is much easier because you're just inputting it. You're not actually doing any math, but in this loop could take a while to run if you have a lot of tests. So essentially what we end up having is, this is our predicted test set. So we have, we predict the first one to be 8, 1, 9, and then we can see how they don't actually match up with like at least the ones we see, they don't match up with the real y test. So we can see our accuracy is actually only 17.6%, which is not great. So we're going to try to see what happens if we use L2 distancing. Will this improve it? So again, just I'll give you another couple minutes to do find distances using L2 norm. The predicted class part is going to be the same code from the previous. I said previous class, I meant previous classes in like object-oriented programming, not as in previous tutorial. But yeah, I'll give you guys 3 minutes until 11:35 to find distances.
Hi, Jake.
Yeah, sure.
I just have a quick question about like the first part. So like
Sure.
yeah, so basically it's the code we're writing yeah, the line like distance, yeah. So I'm just asking like so self.xdr is basically like all images in the xdr, right? So it's like
Yes.
and x so like and it minus only like x index at I, so that's only one image, right? So how can we like use minus like so how can we do this minus between two things?
This broadcast. Yeah, that's important to know actually. So basically, it basically takes every single part of XDR and subtracts this.
Oh,
so
okay.
what this ends up looking like when you do the subtraction is, let me just draw. Ends up looking like you have xi, whatever that, and you have that the whole way down. Does that make sense? It's basically broadcast each part.
Okay. So okay. So like the numpad would do this automatically.
Yeah, exactly. When you do subtractions of different sizes, especially because this size, so x of I colon will still have the 32 by 32 by 3, so it'll be able to tell that it's size 3072, and then it'll know, oh, this is 1 by 3072, and this is like 50,000 by 3072, so it'll just broadcast each of them.
Okay, thanks.
No problem. Does anyone have any other questions? I don't want to be rushing. Just about that part before we go to L2 norms. Okay. So yeah, I'll give you guys a couple minutes to do the distances for the L2 norm, and this should be the same as previously. If anyone's done, just message in the chat and we can continue. Or if you need more time, also just do that. Okay, I'm going to continue. So essentially, the distance is very similar to the other one. Just replace the absolute value with square, and then square root the whole thing after. So itself that xdr minus xi, and then the rest of the dimensions, and then we're summing over axis equals 1, and then we're square rooting every number. And then the y prediction code is just this one from here. Okay. So now we're not going to actually run this version of the code. We're going to use sklearn's k-neighbor classifier. Basically, you input the number of neighbors, and then p, which is your norm value. So p equals 2 would be the L2 norm. So this would be an LP norm. And we'll see how we do using n equals 1. I mean, you can already see it underneath it, but this will take a little bit of time to run because it has to go through each of the ones in the test set and compare using an L2 norm. We could make it run quicker by using, so see we got 35% accuracy, which is much better than the 17% accuracy we got before. However, also note that we only used 200 data points in our test set, in our training set, where in this one we used all of them. So that could also be a reason. However, feel free to play around with this after, and then if you have any questions about it, you could also post on PS and ask, or just so for neighbors equals 5, what this is going to be doing, I can actually I'll run it, I'll explain. So what this is doing is it's actually computing the 5 closest images to it, and then each of these 5 is essentially voting on which one is the closest. And when there's a tie, so let's say the 5 came back and they all guessed different things, it'll just take the closest one. Does this make sense how multiple neighbors will work? And same with 10. 10 would just be the 10 closest images vote on it. Does anyone have any questions on what how that works with k is weirder than 1? Another thing to think about also is if you set k equals 2, would that be any different than k equals 1? If you, does anyone have an answer to that? If k equals 2 will be any different than k equals 1? Then we can try it here. Okay, all the way through, no difference. Yeah, exactly, no difference. So essentially there is, because if they tie, so if it's incorrect, it's just going to take the closest one. If they're not incorrect, if they don't match, the two neighbors don't match, I'll just take the closest one. If they match, it's the same as neighbors being one. Perfect. So now we're going to go over digit classification using the MNIST, and we're going to basically use the k neighbors, and we're also going to compare this to logistic regression. So we went over logistic regression, I think, in practical 2. So I'm not going to go over how that works, but we're essentially going to be using a scikit-learn also logistic regression classifier, and basically we're going to fit it, and then we're going to also time them, and we're going to compare what that looks like. So essentially what we're doing is we're timing how long it takes to fit the training set for KNN, so find the train time, and then how long it takes to predict once you have it, and then we're going to print that. And then for logistic regression, we're also going to take how long does it take to train, and then how long does it take to fit. So while this runs, they want to say what they think is more important between having faster training time versus like, would you rather have a faster prediction time or faster training time if that was the trade-off, and why? Faster prediction, yeah. Why would you rather that?
Because you can just train for once and then use a prediction. Like so if the task requires like really quick prediction, for making like a faster decision, something. Maybe,
exactly. Yeah. So in many real-world applications, the training will be done once, and then you're going to basically be using this model to be predicting multiple times in the future. So if you have something where it takes almost no time, so KNN, we can see it takes 0.01 seconds to train. However, it takes 38 seconds to predict, which is not optimal because let's say we have a bunch of training data, we take it, it trains in 0.01 seconds, but now every time we want to use the model, it takes 40 seconds to run, which is not great. However, with logistic regression, hopefully we can see. Basically, logistic regression will have a longer training time. However, the prediction time should be shorter. While that runs, we're going to continue on just because I don't want to run out of time. So now we're going to try basically an NLP classifier, also predicting on the MNIST data set. And again, this is going to be MNIST is in grayscale, and we're going to normalize the data by dividing everything by 255. And then we're basically going to use NLP classifier, which is an sklearn model, and we're going to plot what the weights look like. So I'm not going to actually run this right now because I already have it run from before, and this is currently running. So essentially, the NLP model we're using has 50 hidden layer sizes. So you guys remember what an NLP looks like from previous lecture, or should I go over that? Okay, for now I'll assume that you guys remember what it looks like. It's basically just a bunch of WTX terms with a bunch of perceptrons, and then separating each perceptron. It doesn't say here, however, there's going to be an activation function that's non-linear, and that activation function is going to be the ReLU activation function. So the ReLU activation function basically looks like it's, I'll draw it out. This is the y-axis. It ends up looking like that, where it's 0 if it's negative, and then just x if it's positive. And this is it's piecewise linear actually, so it's not non-linear. Just it's non-differentiable is the reason that this doesn't work. That this wouldn't be able to be formulated just using WTX. However, this is just piecewise linear. And essentially, each of these layers is separated by this ReLU layer. And then, what we're really interested in is each of the initial 50 layers, and we're going to look at their weights. So, if you here, okay. So I'll go back to logistic regression first. Logistic regression actually did slightly worse. However, we can see that the train time was much longer. However, the prediction time was 0.1 second. So if we have a bunch of prediction times, then that's actually better as a logistic regression model. Even though for this example, it took total more time. In the end, it's fine to use the time to train as long as you know your model is going to be good, and then you're going to be able to predict faster in the future. So to go back to the NLP, basically we're going to do 10 iterations using SGD, which is a form of gradient descent, which we talked about before. And we're going to try to find basically on our training set, we have 98.6% accuracy. Again, this is flattened data set. This is not using the shape. And we're going to, using the weights from each layer, we're going to essentially plot what it looks like. So we can see this is not very big, but you guys can see how certain pixels are darker. So essentially each weight represents the weight that would be multiplied by that pixel. So you have our WTX. I'll draw this. You have WTX. So for each x value, each attribute in x, you'll have a corresponding weight. So you basically have W1, X1, right? Plus dot, dot, dot. And you have a plus B here, I think, sometimes with a bias term. However, I'm just going to look at this part. So we're basically plotting each W where its corresponding X would be. So we can see that the first layer, I think this is at least the first layer. Yeah, the first layer cares more about X's that are in this general area. And the second layer looks at X's in this area, or it cares more about the pixels in this area. And where it's white, it doesn't care about them at all. So basically the weight ends up being 0, and where it's black, the weight ends up being 1. And then when it's gray, the weight ends up being just somewhere in the middle, like 50%. So it's very interesting to see how, like, although this doesn't really make much sense to us, this is how the algorithm, the NLP, is working. Basically by looking at certain parts of the image and weighing them more each layer as the layer goes on. Does that make sense to everyone? What's going on here? Because it's 11:50, so I'm going to leave the last 10 minutes for questions. Does anyone have any questions on this? Because this is pretty complicated, so don't be shy. Or any questions about anything previously as well. How can the k-means algorithm know that there are 10 classes? It doesn't have to know how many classes there are. It basically, all it has to know is it just takes which image is the closest and finds which label it is. So there could be like 30 classes, and if you only give it images from 0 to 9, then it'll only be able to classify those images. Like, you don't actually have to input how many classes there are. You basically, just based on inputting the training data, if it's taking let's say just k equals 1, for example. Wait, you're saying k-means or k nearest neighbors? Because k-means is clustering.
K-nearest neighbor, sorry.
K-nearest neighbors. Oh, no, okay, no worries. Yeah, so for K-nearest neighbors, you're basically just inputting the training set, and you're not inputting how many classes there are. So it just takes the image that is the closest to it, and it outputs the class of that image. So for all intents and purposes, it doesn't actually matter how many classes there are for the K-means algorithm. Like if you input one image, and that was your whole training set was one image, then it would always predict that class because every image is going to be closest to that image because that's the only image in your training set.
Oh, I see. And like so, and for today, like the part where we wrote the code is all correspond to k equals 1, right?
Yeah. So K would be a hyperparameter, but where we wrote the code, this would all correspond to K equals 1 because over here we're taking just one the image with the smallest distance. We're not taking the K smallest.
Oh, I see. So for instance, like if k equals to 3, maybe like
Yeah.
so what will happen here? Like it will just take like it will find the top 3 closest points.
Yeah.
But what if those points labels are different? So it will take
So it'll basically be a voting system. So if let's say 2 of them say the dog and one of them says the cat, then the output will be the dog.
And would there be more weight to the closest point compared to the third closest?
It's if they all tie, then there's more weights to the closest. So if it's 1, 1, 1, then it's whichever one's the closest will be given. But if it's if not, then I think it's just you could change that. And I'm pretty sure in this K-neighbors classifier algorithm you could change how the voting works. But for most algorithms, it's just each 5 because it's a hyperparameter. Each of these 5 or 3 or whatever you do get equal votes. But for 3, the only way it wouldn't be the closest, for example, would be if the other 2 agreed that it was something else. So if the closest one was dog, but the second closest and third closest were cat, then it would predict cat if you had K equals 3.
I see. Okay. Thanks. Thank you.
No problem. One thing also I'm going to go over is basically how RGB could be. Basically, every color could be represented by just 3 images, 3 numbers. That is just going to be so color mode RGB. So essentially, these would be the RGB things over here. So basically, you could say 255, 100, and like 140, and then this would be your color. So adjusting the amount of red to get you from pink to blue, adjusting the amount of green to get you like a nice lime, and adjusting the amount of blue depending on where you are, obviously. So this is just a nice showing on how different number of RGBs change. Does anyone have any other questions about K-nearest neighbors, the timing being why we want a higher training time, about the MLP feature mapping? No one has any more questions. You guys are free to leave. But I'm going to stick around for the last 5 and more if you guys have any more questions. So thank you guys.
Yeah, just a quick remark about K nearest neighbor algorithm. So when K equals to 1, that means nearest neighbor, we're only looking at the closest one. In that case, this is a perfect example for overfitting. So generally, for that case, if you make predictions on the training set, you always get a training accuracy of 100%, right? Yeah, and but this is not the case for K equal to greater or equal to 2, but usually for KN algorithm, we don't care that much about the training accuracy, since in most cases, unless you make K pretty large, usually that would lead to a overfitting of the training set.
Yeah. So basically, this, if you're doing this on the training set, then this will be the same as this. Your pixel-wise absolute value difference or your L2 norm difference will be 0. And then that's obviously going to be the smallest distance. Therefore, your training accuracy is going to be 100%. Whereas it wouldn't be the case in logistic regression or MLPs.
Yeah, and we're applying actually K into a relatively high dimensional case, which is image classification. That means we really having at least 32 by 32 or this kind of dimensions in our training data. But here's another example of lower dimensional case where you can actually experiment around with a different number of neighbors, which is K, and also different metric and stuff like that to see how like different configurations of the model can change it.
Yeah, and prediction time would increase if K increases because it has to predict for, or it would increase not that much because you're still computing the distances. Like when we do this, you're still computing the distance for every data point. So by finding K, you're basically just finding the K closest ones here. So it will increase very slightly, but not substantially. Okay. The biggest thing is because you have to find the distances for every single point, even to know which one the closest is. This is the part that has the most. And you're doing this for obviously for every image.
Exactly. And if you're playing around with the code we provide in the lab 10, pay attention to the handwritten code for K where K equals to 1. Do not directly implement it with the entire train set and entire test set. Because if you use with the entire train set, predicting on each individual prediction might actually take 1 second to do so. So it might take longer than you expected. Feel free to reduce the train set and test set for your convenience.
So that's also something important to know. Yeah, even though the training time the training time won't depend on how big the training set is. The prediction time will depend on how big the training set is. And same with the test set. So just because this is fast doesn't mean that you should necessarily doesn't mean that more training data is necessarily going to make it not going to change the speed, because the training data also impacts the prediction speed for K-nearest neighbors, where it doesn't for logistic regression. Yeah, so this would be basically just a nice little how this changes. Yeah. We got to the distance test image to the mean of K clusters. And find the nearest process of the K mean. Yeah, so you could do some sort of K mean clustering where you basically take the mean. Yeah, that is a method of doing image classification. However, it would be similar to K-nearest neighbors. And then, but you essentially, what clustering is important for is you don't have the labels. Where image classification like this, you will have the labels. So in this, we have that it's an airplane, automobile, bird, cat, whatever. However, if you do it like the way you said with K clusters, you could basically take all these images and find, say, okay, we know there's 10 clusters. Which images are part of each cluster? And then that is an application of clustering if you don't know the labels. So that wouldn't be for finding, like if you had a test set and you wanted to find where, oh, I have this new image. Is that a boat, a cat, or a dog? This would be more, oh, I have a bunch of these images. Can you tell me, like could this algorithm tell me what are they closest to? So this is a car, it would be closest to this car type thing. That makes training time slower, prediction time faster. K-means clustering is different because it's unsupervised learning. It's very different applications of like it's not the same. Like this would be like there's no really prediction and training in K clustering. It's just one algorithm because there's nothing to train on because you don't have any labels. Any other questions?
Hi. So I've been playing around like with the link you sent, like about the cake, like board. Yeah. So I'm just this board. Yeah. So like, so what's the white area like in this graph?
Graph actually has explanation. So points that are colored white are because of the tie. Yeah.
Oh, okay. Thanks.
Yeah, but as Jake has mentioned, there are different ways of treating ties. One of the ways was to classify it to the nearest one.
Oh,
but there are also others like randomly pick or other ways of treating ties.
Yeah.
Okay. Thank you.
Especially with number of K's equals 2.
Thanks.
Thank you.
No problem. Any other questions? Sure.
No, I'm good. Thank you.
Okay, perfect.
Bye.